Hi, everyone. Welcome to this seventh and final lecture in the practical introduction to quantum computing. First of all, I would like to say thank you to all the people who have taken some time to answer our feedback survey. You know that it will be open for some days yet. So if you have the time and you have not answered the questions, we would love to hear from you, to have your feedback. We have many suggestions for new future lectures and courses, and some suggestions to improve the lectures and everything. So this is always very helpful to us, and we appreciate if you take the time to fill out the survey. Okay. I would also like to answer one question that has been repeatedly appeared in my inbox in the last days since the lecture last week, which is about quantum machine learning and what is possible to do with these techniques that is not possible for classical machine learning. And well, this is a complicated question. This is something that I also addressed at the beginning of the course regarding quantum computing in general. I mentioned that we really don't know how to prove that quantum computing is certainly more powerful in some sense than classical computing. We cannot prove that there is a speed up for certain problems, basically because we don't have the mathematical techniques. In fact, we don't have the mathematical techniques to even prove that P is different from NP, something that we strongly believe to be true. And quantum computing should be somewhere there in the middle. So if we could find a separation between classical and quantum computing, that would most certainly also imply a separation between P and NP, or similar problems in complexity theory that we do not know how to answer yet. Okay, and for quantum machine learning is the same. If we could prove that quantum machine learning is more powerful for some tasks than classical machine learning, then we would have that kind of separation that we don't expect to be able to mathematically prove in the near term. Okay. Also, the other possibility would be to show in practice with some task using current quantum computers that we can obtain some better results and some advantage by using quantum machine learning. And this is related to some of the topics that I will be covering today. It's related, of course, to quantum supremacy. But again, we have the difficulty of having very small and noisy quantum computers. And also the challenge that classical machine learning has done so well in the past, and we have so powerful techniques that it's very difficult to beat them at their own game. So the kind of applications that I have been presenting in last lecture and one that I will be presenting today do with quantum machine learning, with the use of quantum techniques in machine learning. For instance, I told you about the possibility of using HHL, the HHL algorithm, to speed up some classical machine learning techniques. And also we have this other possibility of using the high dimensionality of the Hilbert space to have some advantage in expressibility. And there were some results that I commented last week, preliminary results about, well, the Fisher information of quantum neural networks, but it's all work in progress. We have nothing definitive yet, but I mean, it's almost the same as with quantum computing, but quantum machine learning is still, it's even younger than quantum computing in general, okay? So I think it's interesting to learn what are the things that people are trying, especially in high energy physics, which are the experiments that researchers are conducting. But you have to see these results as preliminary work, as proofs of concept that will lead us to understand better what are the capabilities of machine learning. Okay, so nothing definitive yet, but I think a lot of promising directions for research and for practical applications in the future. And then let me go back to the slides and talk a little bit about one of these applications of quantum techniques in machine learning. And this is what is usually called quantum generative adversarial networks, which of course is the quantum version of the famous GANs, generative adversarial networks, that were introduced, if I'm not mistaken, in 2014. And since then have become extremely popular. These are machine learning models that instead of trying to learn a classifier, like for instance, the QSVM or the quantum neural networks that we talked about last week, they try to learn a distribution from some real data that we have. And usually this distribution is very difficult to define mathematically, or probably even there is no clear definition of what is this distribution, but we usually have a lot of examples. One of the applications in which these GANs have excelled is the generation of human faces. You see here some examples of the result of GANs generating human faces. None of these people are real. They are all generated, but they look completely real. I mean, it's very difficult to differentiate them from real images of real people, okay? So this has been a very active field of research in machine learning. And in the last few years, also researchers have tried to incorporate quantum techniques in this field of generative adversarial networks. How to do that? Well, first we need to learn a little bit to talk a little bit about what is the architecture of classical GANs, and then we will see how to modify slightly this architecture in order to incorporate quantum computing. Okay, so the idea is very simple, but at the same really interesting. In a generative adversarial network, in a classical GAN, we have two different neural networks. One is called the generator, the other one is called the discriminator. And the idea is that they are trying to beat the other neural network at a game. The game is that the generator tries to generate, of course, images or whatever kind of data you are trying to learn to reproduce. And the discriminator is trying to differentiate the real images or the real data that comes from your training data from the data that is generated by the generator, okay? And this is a game in which the generator tries to fool the discriminator to accept the data that this generator is creating as real, while the discriminator is trying to differentiate the real data from the data generated by the other neural network, okay? To do this, we usually train the neural networks in alternative phases. So we fix, for instance, the discriminator, and then we feed into this discriminator data taken from the training data set and data taken from what is generated by the generator. And then we feed this into the discriminator. The discriminator classifies the data into real or fake, and depending on the answer, then we modified, for instance, the parameters of the generator if we are training the generator, or the parameters of the discriminator if we are training the discriminator. In order to do that, we define some loss functions, which are kind of symmetric, and although in practice sometimes they are not used in a symmetric way, but these functions, the discriminator tries to maximize them and the generator tries to minimize them. For instance, we can define the most typical way of defining these loss functions for the generative adversarial networks is to use this loss function here, in which D stands for the level that the discriminator outputs on a certain input, and G stands for the data that is created by the generator. So what the discriminator tries to maximize is the probability of classifying the real data as real and the fake data, the data generated by the other part of the GAN, as fake. So in order to do that, we can compute the average of the over all possible real data of the levels that the discriminator outputs, and also this other part of the function in which we try to maximize the probability of the discriminator outputting level fake for the data that comes from the generator. Okay, so you see here that, for instance, if we define level real as 1 and level fake as 0, then we try to maximize this part here. We want to make this D of X as big as possible, because then for real data, we are outputting level 1. And we try to make this big, which is the same as doing this small, so close to 0. So D is going to output 0 for the data that comes from the generator. For the generator, is the other way around. The generator tries to fool the discriminator. So we want this to be minimized. We want this output of the discriminator on the input generated by the generator to be close to 1. So this is going to be minimized. So this is similar to the same term that we have here in this loss function, but in practice, sometimes we change this to this other function that in this case we want to maximize, because we want this to be close to 1. And this is just for practical reasons, because it is easier to compute, or the gradients behave better in this case, and it's better for the training. So the idea is that the generator and the discriminator are competing in this game. The discriminator tries to separate the data generated by the generator from the data taken from the real training data set, while the generator tries to fool the discriminator. Okay, how to do this in the quantum setting? Well, the idea is that we have two different neural networks. So what we can do is to substitute one of these classical neural networks, or both, with a quantum neural network, a variational form of the kind that we were using last week for quantum classifiers, for instance, for quantum neural networks. There have been several different proposals of what is a quantum GAN, a quantum generative adversarial network. You see here two of the first papers that were published in this topic, and you see that the publication date is very, very close, and there are several other different proposals for what is a QGAN. Again, as I told you last week, the terminology is still not very clear. There are slight difference between one proposal and the other, but well, the main idea is the same for all of them, is to take this architecture of the classical GAN and then changing some of the neural networks, or both, one of them or both, to be a variational circuit. Then the structure, or the actual variational form that you use for the quantum neural network can be different, but the main idea is the same. And what I'm going to show as an example with a notebook is one of these proposals that was published by researchers at IBM, in which they use this quantum version of the generative adversarial networks to learn a random distribution. In this case, it's not images, although there are, I will show you an example. There are proposals to use this to generate images, but in this case, what these researchers did was to have an initial probability distribution, and then to learn how to generate this kind of, how to sample from this kind of distribution with a quantum generative adversarial network, okay? This is an interesting problem because in general, if you need to load a distribution in a quantum circuit, there is no efficient way that we know of to do this in general. So if we have a general distribution, there is no polynomial algorithm that creates a circuit who is able to sample from this distribution in general, okay? So this is a useful task that can be more or less successfully tackled with this proposal of a quantum generative adversarial network. And a similar approach was used in other papers. For instance, in this case, what we use, or what they use, is this particular form of the variational circuit, in which you have rotations, in which you also have a part that creates entanglement. And this is the typical definition of a variational form. I showed you some other possibilities last week, and the details can change slightly from one proposal to other, but usually we have these parameterized gates, some entanglement, and then we can repeat some of the layers. And you can find more details about this proposal in this paper I showed you in the previous slide. And this is the kind of architecture that was used here at CERN Open Lab in order to reproduce images that come from the detection done in calorimeters when you have particle collisions. This is something that has been done traditionally with Monte Carlo methods, and in the last few years, CERN Open Lab has been working extensively in doing this kind of generation of events or results of events with classical generative adversarial networks with a lot of success. And in 2020, I think, researchers here at CERN Open Lab, including Sofia Valecorsa and Soo-Young Chang, starting looking into the possibility of using not classical generative adversarial networks, but quantum generative adversarial networks. This is a difficult task because training this kind of model also in the classical setting is quite challenging. And in the quantum setting, you have even more difficulties because, well, we don't have the computing power either in actual hardware or with simulation to do this at a large scale. But as you can see here, the results, or the preliminary results, are quite kind of promising. At least it is possible to reproduce qualitatively, although not exactly quantitatively, the results of real data with the generated data that comes from the quantum version of these generative adversarial networks. And at CERN Open Lab, we are working on modifications of these models with also in collaboration with Cambridge Quantum Computing, and this is an active field of research which is of great interest to us. So I don't know if there is any question about this. Okay, then I will show you how to run one of these quantum generative models with IBM Qiskit. So as always, in the last few lectures, I'm going to use an implementation that is already included in Aqua. So you don't need to define all the circuits, all the gates one by one. You can use this already prepared definition of the algorithm and parameterize it with your own data. But in this case, I'm not going to run it directly because it takes quite a lot of time. And also, I warn you that this notebook is not working correctly with the current version of IBM Qiskit. This is something that I noticed a few weeks back. I reported this to IBM. They are looking into this. There is some change with the implementation of the QGAN that makes this not learn correctly. So what I did was run it with a previous version of Qiskit in which it works correctly. So I have uploaded to the Indico page both the notebook with results for you to see what is the expected output of this algorithm, and also the clean version without results that you can try to run if you have an older version of Qiskit. For instance, here I have run this. I have included this instruction in order to know which is the version that I'm running. For instance, you see here that I was using 0.19.6, while the current one, I think it's 0.23.1 or 2, okay? And this problem has not been corrected yet. I hope that it will be corrected soon. But if you have this older version, or if you install this version in a separate machine or whatever, you can run it and obtain these results, okay? So what I'm doing here is a very, very simple task of learning one of these random distributions I was telling you about. And what I chose was just a simple binomial distribution, which after sampling gives me this histogram here, which is the data that I'm going to use in order to train the network. Now, what I can do is to use the implementation in Aqua for the QGAN and define what is the real data that I'm going to use, the number of qubits, how many examples I want to use in each of the phases of the epochs in which we train the generator and the discriminator, what is the number of times that I'm going to train the discriminator and the generator, these bounds which are needed in order to know what is the lowest value that it's supposed to be generated and the highest value that is going to be generated. And then with a quantum instance, I can run this algorithm and obtain samples from the generator that has been trained in order to compare the output of the network with the training data. Okay, so in this case, what I obtained was this histogram, which is very similar to this one. And in fact, you can see that during the epochs, the generator and discriminator change the value of the loss function, but they oscillate around a value which is typical for training of classical generative adversarial networks. And also you see that the relative entropy, which is a measure of the similarity of the, or the distance between the real data and the generated data, it's going down steadily until it reaches a value which is close to 0. So this is why this was learned by the model, and we can use now this model, this quantum circuit. We have a quantum circuit that we can use in order to sample for this distribution, okay? If you train it with the current version of Qiskit, you are going to see that the problem is that the relative entropy does not decrease, and then what you obtain here is not similar to what you expect. So there should be some small bug somewhere, and once that it is corrected, it should be worked again as expected. Okay. Any question about this notebook, this application? Okay, let me go back to my slides. Okay, so this is all that I wanted to show. I wanted to show you about quantum machine learning. Of course, quantum machine learning is a very active field, and there are many new developments and different models that I have not covered. If you are interested in learning more, I have cited here two recent papers which are surveys of how to use quantum machine learning in high energy physics. So you can check them in order to see more applications, and maybe it's interesting to you. So I have some feedback from the people in the Zoom room. So Richard Olivka says that he has locally installed 23.1 and the entropy converge faster than yours, but it doesn't seem to be broken. Okay, so that's good news. Probably I didn't update correctly, or well, I don't know. I checked with the IBM Quantum Experience a couple of days back. For me, it does not come. Bogdan Vulpescu says, for me, it does not converge and the distribution is not okay. Also with Qiskit 23.1. So maybe the problem is with Aqua. Maybe we should check the version of Aqua, which is in which this is installed. But well, there seems to be a problem, but it used to work, as you have seen. So it should be resolved soon, and it should be working again. Okay. If I learn how to do this, probably I will post an update on the Indico page or something. But thank you for the feedback. Okay, so as I told you, this is more or less what I wanted to say about quantum machine learning. There are more models. You can check these surveys. For instance, this one has a co-author, Sofia Valecorsa from CERN Open Lab. And there are many different papers cited into these two surveys, which you can take a look into if you are interested in quantum machine learning for high energy physics. But now I want to move to a different topic, which has been implied in all that we have been doing so far without being mentioned explicitly, which is the problem of noise, the problem of errors, and how to try to correct them in order to obtain fault-tolerant quantum computing. Quantum computers and quantum algorithms that are not affected by noise, that are not affected by errors in the gates and other problems, errors in measurements and things like that, okay? So this is a problem, the problem of creating fault-tolerant quantum computing or quantum computation that has been important since the beginnings of the theory of quantum computing. And some people at the beginning thought that maybe this problem was really impossible to solve, and it was going to be something that was a big challenge, a real obstacle for obtaining a speed up with algorithms like Shor's algorithm or Grover's algorithm or the other methods that were being proposed at the time, okay? Why to think that maybe we cannot correct the errors in quantum computing? Well, we have several reasons to think that. For instance, we have the no cloning theorem. So you know that in classical computation, the basis of or the main technique that you use in order to correct errors is to be able to have redundancy, so copies of the same information. So if one of them gets corrupted, then you can use the others to correct the one that is incorrect. So in quantum computing, it seems that we cannot do that directly because we cannot clone information. So that is a problem. Another problem is that, well, in order to check whether the information is correct, it seems that we need to measure the information. And then what we have is a result, but also the collapse of the state vector, and then we lose, or may seem that we lose some information. Okay, and also there is another obstacle that people have mentioned, and it's also a problem, and it is that compared to classical computing, here we have not discrete operations. We have not just zeros and ones, but we have a continuous of values. So also the operations are continuous. These rotations depend on parameters that can be real numbers. So maybe slight modifications, slight imprecisions in the implementation of these rotations can add up, and at the end, we have something that is completely different from what we expected, okay? So these seem to be rather serious problems, but fortunately for us, and maybe even surprisingly in some sense, we can define quantum error correction and we can define the idea of quantum fault-tolerant quantum computation with a beautiful theory of quantum error correcting codes. Okay, I'm not going to give you here the full details of what is quantum error correction, because this would extend for at least 7 lectures or more. Okay, so this would deserve a course on its own, but I want to give you at least the taste or the flavor or what you can do in order to try to correct these errors that may rise. And I will do this first by introducing a very simple idea from classical error correction. And I will show you how to translate this into the quantum domain, how to do this kind of code in a quantum setting, and then how to improve or combine different ideas in order to obtain better codes, okay? So the most typical way, or the simplest way of trying to correct errors in the classical setting is, as I told you before, by using redundancy, by using multiple copies of the same information. So imagine, for instance, that you want to transmit a bit over a noisy channel, or to store a bit in memory, but there may be some noise, and then this memory can get corrupted, or the bits there can flip. So you want to be sure that after some time, when you try to recover this information, or in a classical channel, information channel, the other person that is receiving the information receives the correct bit that you want to send. So in this case, what you can do is, for instance, store the same bit 3 times, or send the same bit 3 times, okay? So with this, what you gain, the good thing of using this kind of code is that now, in order for this information to get corrupted, 2 of the bits must change, okay? Because if I send the bit 3 times and only 1 of the bits change, I can use the majority vote in order to correct the error that has occurred. So provided that only one error occurs at most, I am able to correct the information, to restore the correct information by using the majority of the results. For instance, if I'm sending these 3 bits to from Alice to Bob, and Bob receives either of these strings here, then he corrects the information back to 0, 0, 0, okay? Assuming that at most one bit has been modified, 1 bit has flipped. And with the same idea, if he receives 1 of these 3 strings, then he can correct to the correct information, provided that at most 1 of the bits has changed. This is the simplest idea that you can use in classical error correction. Of course, there are other techniques much more evolved and complicated than this one. There are many different classical error correcting codes, but the idea is more or less the same. You have some redundancy, some multiple copies of the same information, and from this majority you can restore the correct values, provided that not much of the bits that you have used have been modified in the channel or have been affected by noise. Okay, so the idea is in the quantum setting to try to do the same with the basic states that we use to define information. Okay, so if we think about the information in just one qubit, we know that we have the state 0, state 1, from which we can define general superpositions, which are the most general states of a qubit. So what we try to do is, well, instead of using just one qubit to store the information, we are going to use 3 qubits, okay? And then we are going to use this state, which is composed of 3 zeros, to denote this state 0, and we are going to use 3 ones to denote the original state 1 of the qubit, okay? So we are using again redundancy in order to store the information or to send the information. So what we have here is now what is usually called a logical qubit, qubit represented as 3 physical qubits. Okay, so the amount of information that we have is just 1 qubit, the logical qubit, but we are using 3 physical qubits. Okay, so we need more qubits in order to store this information or to send this information and protect it against errors. Of course, then we can use linearity to define what is the encoded state of a general qubit, which should be the superposition, the linear combination of the codes that we use for the basic states. Okay, so a state like alpha 0 plus beta 1, it's encoded as alpha, the encoding of 1 0, that in this case is 3 zeros, 3 physical qubits in the state 0, plus beta, the state that encodes the logical 1, which is 3 qubits in the physical state 1. Okay, and notice that this does not violate the no cloning theorem, because we are not doing 3 independent copies of the state of this qubit, which would be impossible, but we are using, for instance, this circuit here to create entanglement. Okay, so we are not using independent copies, but entangled copies. And if you check the different possibilities for the input side here, you will notice that what you obtain is exactly what you need in order to encode the information. You only need to use these 2 CNOT gates, and of course the 0 is going to go to 0 0 0, and the 1 is going to go to 1 1 1. So this is one way of encoding the information, which we can use to realize this simple code. Okay, how is this useful? How can we now use this in order to correct errors, to prevent the information from being corrupted by noise? Well, the idea is that now we would like to check whether in the state that we have, all the values in the states are the same. So we should have 0 0 0, and if we detect that we have 0 0 1, for instance, then this is not correct, and we would like to restore the information to the correct value. This is where one of the problems or objections that I mentioned at the beginning manifest itself. The idea that, well, if we measure now this encoded state, then we destroy the information that we have, because If we measure, for instance, the 3 qubits here, we are going to obtain either 0, 0, 0, or if there has been some error, 0, 0, 1 or whatever, but we obtain this result at the cost of losing the information about alpha and beta, okay? So this is not something that we want to do, because then we lose the information trying to check whether there has been an error. So what we can do is to measure partial information about the state. We don't want to measure the whole state, but we want to do just a partial measurement that gives us information about whether the values that we are using in the encoding have this property of being all of them equal or not, but without learning any other information about the state, and without collapsing the state to something that loses the information that we were storing there, okay? So what we can do is to use this clever circuit here in order to check whether the bits, the qubits, are equal one to the other, have the same value or not, and also to have information of which qubits are different. So now we can correct the results back to the correct information. So what we do here with, for instance, this first part of the circuit is to compare the first qubit and the second qubit. We use an auxiliary qubit in order to see whether these two qubits are equal or not. So what we do here is to flip this auxiliary qubit conditionally on the value of this first qubit, and we also flip it again conditionally on the value of the second qubit, okay? So notice that if both of them are 0, then we are not going to apply the NOT gate here. So we are going to have 0 again. If both of them are 1, then we are going to flip the qubit to 1 with this C0, but we are going to flip it back again to 0 with this C0. So if both of them are equal, at the end of these two operations, here we are going to have 0. And if we have 1, we know that these two qubits are not equal. These two qubits, one of them is 0 and the other one is 1. We don't know which one is 0, which one is 1, but we know that they are different, okay? With this second part, what we do is the same, but now we compare the first qubit with the third qubit, okay? So again, if both of them are equal, here we are going to have 0. If both of them, if they are different, we are going to have here 1, okay? So now we are going to have here 2 bits of information we can measure here, and we are going to have 2 bits of information. The first one tells us if these 2 qubits are equal or not. If this is 0, the 2 qubits are equal. If it is 1, they are different. And this result of the measurement here, it's going to tell us whether the first and 3 qubits are equal or not, okay? And then we have these 4 situations depending on the result of that measurement. If all the qubits are equal, then we are going to obtain 0, 0 as the measurement of these 2 ancillary qubits. If, for instance, the third one is different, then you know that the first and second one are the same, and then we are going to obtain 0 here as the first result. But since the third one is different from the first one, then we are going to obtain 1 in the second ancillary qubit, okay? And the same is the results for all the different cases are similar. If the first and second one qubits are different, but the first and the third are equal, then we obtain 1, 0. And if the first is different from the second and the third, we obtain 1, 1, because of course then the first is different from the second and the first is different from the third, okay? So now, provided that only 1 qubit has been flipped, by measuring this information, we know which is the bit that is different, okay? If we obtain 0, 0, nothing has changed. And if we obtain 0, 1, we know that the third qubit is the one that is incorrect. If we obtain 1, 0, we know that the second one is incorrect. If we obtain 1, 1, we know that the first one is incorrect. And then we can use that in order to restore the qubit back to its correct value by applying an next gate conditional on the results that we obtained here, okay? So this is exactly what we need to do. If we obtain 0, 0, we do not change the state. If we obtain 0, 1, we apply a next gate on the third qubit and so on, okay? So once that we measure this, we know how to correct the information back to the state that is consistent with the coding that we are using. In fact, this is doing even more, okay? Because, well, you may think this only works if exactly one of the qubits change from 0 to 1 or 1 to 0. But what happens if instead of a rotation of p degrees, what we obtain is a rotation, what the error is doing is a slight rotation that changes the 0 a little bit towards 1, but not completely towards 1, okay? Well, it seems it turns out that this is also corrected by this code because somehow when we measure the ancillary qubits in order to obtain what we call the syndrome, these 2 bits that reflect what is the error that has occurred, when we measure those ancillary qubits, we are somehow discretizing the error. So the most general situation that we can have in which one qubit turns a little bit from 0 to 1 or to 1 to 0 is, for instance, this situation here. So imagine that the third qubit is the one that changes, but it changes just a little bit towards 1, and it is still in state 0 with some amplitude, okay? So imagine that this is very, very small, okay? So we have a small error. So we have this state which is not correct because it's not something that encodes real information, because in order to encode real information, these 3 qubits should be the same. But we only have here a small deviation from the correct state. So it seems that since it has not changed completely from to 1, maybe we cannot correct this. But notice that when we applied the ancillary qubits in order to measure the syndrome, what we do is to entangle each of these possible basic states with its syndrome. So for this, we are going to obtain syndrome 0, 0 because the 3 qubits are the same. And for this part here, which is part of this superposition after the error has occurred, we obtain the syndrome, the correct syndrome for this part, okay? And this is entangled with the corresponding state of the qubits that is compatible with this syndrome. So when we measure now these qubits, we are going to obtain either 0, 0 or 0, 1. And since this is entangled with the other part of the state, if we measure 0, 0, 0, then the rest of the state is going to collapse to 0, 0, 0. And if we measure 0, 1, the rest of the state collapses to 0, 0, 1, okay? So somehow in the process of trying to see what is the error that has occurred, if any, we are realizing a concrete discrete error. Before that, we had a superposition of errors, or in this case of no error with error. But when we measure, we realize either a situation in which no error has occurred, if we measure 0, 0, or in which an error of a complete flip of one of the qubits has occurred if we measure 0, 1. And then we can correct. If we obtain 0, 0, we do nothing. If we obtain 0, 1, we flip this qubit back to the 0 state, okay? So I think this is a a very, very nice idea, very also surprising property in some sense, that when we measure in order to see what is the error that has happened, then of the possible superpositions of errors, here I'm showing only 2 possible errors, but you could have many different possibilities, in this case up to 4. And if you use a bigger code, you have many different possibilities for errors. But when you measure, only one of them is the one that gets actual, because the measurement collapses the state to that exact error, and then you can correct it. So I think this is really very interesting and a very nice idea, and something that gives us the possibility of implementing these quantum error correcting codes. So, well, this works for the flip of a single qubit. So if we have an error of this kind that changes a 0 into a 1, but of course, this is not the only kind of error that can happen in the quantum setting. In the classical setting, since we only have the values 0 and 1, the only kind of error that we need to take care of is the change from 0 to 1 or from 1 to 0. But in the quantum setting, we can also have other different modifications of the information. For instance, if the phase of one of the parts of the state changes, for instance, from +1 to -1. Okay, so here we were dealing with the errors that occur when an X operation, a NOT operation, is applied to one of the qubits. And here we have to deal with the error that occurs when a set operation, an unwanted set operation, because of the interaction of the qubits with the environment or with other qubits, happen in an uncontrolled way. Okay, so imagine now that we have this qubit and it changes to this other state, which is different. In fact, is orthogonal, because a set gate has been applied in an unwanted or uncontrolled way to the information. Okay, how can we protect against this kind of error? Well, what we can do is to define a different code in which now the 0 is encoded as the tensor product of 3 plus states. Remember that the plus state is the superposition 1 over the square root of 2, 0 plus 1. And the 1 is encoded as the minus state, which is the superposition 1 over the square root of 2, 0 minus 1. Okay? So why do we use this encoding? The idea of using this encoding is that the set operation now changes the plus into minus and the minus into plus. So the set operation on these states acts like the X operation was acting on the 0, 1 states. So we can use exactly the same ideas that we use to protect against the flip of a qubit, to protect against these phase inversion errors by using this different encoding. Okay, so what we do in order to encode a general qubit into the superposition of the encoding of the basis states is to use a circuit which is similar to the one that we used to encode in the first quantum error correcting code that we defined. But now, in addition to that, we use the Hadamard gate. So here we would have that the 0 is going to be transformed at this point in 0, 0, 0. The 1 is going to be transformed at this point in 1, 1, 1. And then if we apply this Hadamard gates, we know that the 0 goes to plus and the 1 goes to minus. Okay, so if we have here 0, 0, 0, then after the Hadamard gates, we are going to have plus, 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 which is what we want. If we have 1, 1, 1 here, after applying the Hadamard gates, we are going to have here minus, minus, minus. Okay, so this is a circuit that does this encoding for a general qubit. And now, in order to detect whether one of these phase inversions has occurred, what we can do is notice that the operation of the X gate is exactly the same as the operation of the Z gate, but with a Hadamard gate before the Z gate and another Hadamard gate after the Z gate. This is something that we have used before. If you don't remember, you can easily check by multiplying the matrices for these operations. But this is something that we can use because now, imagine that the error that happens here is a Z gate, okay? So we have encoded our state with this part of the circuit. Now, in one of the qubits, we have a Z gate that we did not want to have. So how can we detect that Z gate? What we can do is to use another column of Hadamard gates, and then the error that we have here, it's going to be equal to a qubit flip that like the one that we were taking care of with the other quantum code. Okay, so here, if the Z is at this qubit, we are going to have an X here, and then we do not have errors in these two qubits because we are supposing that only one of the qubits is affected by the error, and then the Hadamard gate cancels with the other Hadamard gate. This Hadamard gate also cancels with this one, and what we have from this part is just an X gate acting on this first qubit. Okay, but here this is the way we use the circuit that we use in order to code for this quantum error correcting code that protects against X errors. So then we can use exactly the same syndrome that we used in order to protect against X errors, against qubit flips. And then we can detect the syndrome here, correct the syndrome, and then restore everything back to the plus, 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 minus, minus coding that we were using, okay? So exactly the same analysis we were using here is the one that we can use in this new quantum error correcting code by taking into account that here we have H set H, which is an X operation. And again, of course, in order to correct the error, we take into account the syndrome that we have measured, and then we apply the operation that we need in order to correct that phase inversion that we have. The Z operation is its own inverse, as well as the X operation is its own inverse. So we can apply a Z to cancel the Z that has occurred. If we measure 0, 0, there is no error. If we measure 0, 1, it means that a Z has occurred on the third qubit. So we apply another Z to cancel that on the third qubit, and so on. And again, we can use this trick of the discretization of the errors in order to correct for errors that are a rotation around the Z axis, which changes a little bit the phase, but not completely from +1 to -1 or from -1 to +1. Okay, because again, when we use the circuit, this part of the circuit, to detect the syndrome, when we measure, well, of course, we are going to have a syndrome that is entangled to the kind of state that we have in that situation. For instance, here we have no error. Here we have an error in the second qubit. But when we measure these two qubits of the syndrome, again, we collapse the state to a concrete error. And that concrete error is what we can correct with the corresponding Z operation. Okay, so it's exactly the same idea. Any question up to this point? Okay, so I think that the best way of seeing what is happening here is to have a circuit implementing these quantum error correcting codes to cause an error in some of the qubits and see what is the syndrome and how we can correct that in that situation. So I'm going to use Quirk in this case because it's very visual. Of course, you can also implement this in Qiskit, but I think it's more useful to see it this way. So let me go change my screen sharing to my browser, and then let me maybe make this a little bit bigger. Okay, and let me show you here what happens. Okay, so this is the quantum error correcting code that protects against flip of one of the qubits. Okay, so this is the part in which we encode, and I have included here these visual indicators of what is the situation of the qubit. Okay, so now we are encoding the 0 qubit, so here we have 0, 0, 0. Okay, and now we have an error here. This is an X gate.
Yes.
Yes?
We don't see your browser.
You don't see it? Oh, let me. Oh, sorry. Okay. What about now?
That's fine.
Okay, thank you. Sorry about that. I thought I had shared the correct window, but I didn't. Okay, so let me start once again. So this is the implementation of the code that protects against flip of one of the qubits. So this is the part in which we encode. And after this, I have included these visualization tools in order to see what is the state of the qubit. So here I'm encoding the 0. Okay, so here I have 0, 0, 0. Okay, and then I have an error here. This is a qubit flip that I didn't want to happen. And after this error, I have here, of course, the state 1, 0, 0, which is not one of the states that encodes correct information. So I know that there is an error here. Okay, something has happened. One of the qubits has flipped, and we have a state that is incorrect. So then we use the measurement of the syndrome, or the evaluation of the syndrome. And notice here that after this evaluation of the syndrome, the qubits that are used as auxiliary qubits to compute the syndrome are now set to 1, 1, which was the indicator of a flip in the first qubit. Okay? If the error happens, for instance, in the second qubit, notice that now the syndrome has changed. So now I can see that the syndrome is 1, 0, which corresponds to a flip of the second qubit. And if the flip happens in the third qubit, then I have the syndrome 0, 1, which is the indication of a flip in the third qubit. Okay, so, and of course, if I don't have any error, then the syndrome is 0, 0. Okay, so imagine that I have that, that error there. Now, depending on the syndrome, I can correct with this part here. Okay, so it's very easy to check. This is an exercise for you, that depending on the syndrome, with these operations here, these control C nodes, I can restore the qubit to the 3 qubits to a correct situation once again. In this case, to 0, 0, 0, which was the original situation. Notice that I can also do this if I'm encoding the 1. Okay, so notice that here I have 1, 1, 1. Here, this is an error. But after detecting the syndrome and correcting the error, again, I have 1, 1, 1 here. Okay, and if I change here, if I have just one error, the syndrome changes, but the final state that I obtain here is still 1, 1, 1, which is what I want. Okay, I can also have this even if I have a superposition of 0 and 1. Well, in this case, it's a little bit more difficult to see, but you can check with these situations here that what I have is again a superposition. Okay, so this works. Bilinearity works also for superposed qubits. What it does not protect, what this code does not protect against, is against 2 changes. If I have 2 errors, if I have two errors in two independent qubits, then what I correct is by majority rule, I correct to an incorrect information. So I'm assuming that only one error has occurred, and then this should be the 111 state. Okay, so this is something that is a limitation of the code, and in any error correcting code, you have this kind of limitation. If you have more errors than you can correct, then what you obtain at the end is not the original values. Okay, but the assumption on this kind of model is that at most one error occurs in the qubits, and these errors are independent. Okay. You can also see that there is a question, but I will answer it in a moment. Okay. You can also notice that if you have a rotation around the x axis, which is not a complete flip, but something in between, the syndrome changes. I mean, the syndrome is a superposition, what we saw in the slides, but then these corrections here work. Even if you have just a slight change or something that is maybe close to a complete flip from 0 to 1 or from 1 to 0, if you have coded a 111, what you obtain here is correct because of this discretization that I showed you. Okay, so this is a very, very nice property. There is a question, which is, does it mean you have a 5-qubit gate just before the end? Well, this here is a way of denoting three different 3-qubit gates in which we have, well, we could say that they are 3 Toffoli gates. So they are 3 NOT gates controlled by these qubits. Okay, so you could do this independently. Let me do it like this. You could have also this, which is exactly the same. 3 independent qubit gates, 3-qubit gates, Toffoli gates. Sorry, this should be controlled by this. Okay, and the effect is, of course, the same, but I just use it together to have a shorter circuit. Okay. Okay, I don't know if there is any other question about this. Okay, so then let me show you the other. Where is my okay, here. The other code, the phase inversion correcting code. Okay, so let me select the browser. Okay, can you see the new code?
Yes.
Okay, thank you. So the idea is the same, but now we have this correction, this encoding here. Now the error is a set gate, okay? And again, if I change it, the syndrome changes. And now the corrections that I must apply are set gates instead of X gates, but the rest of the code is, or the circuit is the same. If I change this for a rotation around Z, again, you see that I'm protected against that kind of error. Okay, so it's the same idea. What I'm not protected against, of course, are 2 independent errors, okay, or 1 error of the incorrect kind. Okay, well, this should. Okay, this changes the phase. We cannot see it here, but this changes the phase of the qubits, and this is something that I'm not protected against. Okay, and the same happens with the other code. It does not protect against flips of the phase, inversions of the phase. Okay, so we need something that protects against both kind of errors. But because if I only use one of the codes, then I'm protected against one kind of error, but maybe the other one is happening. And if I choose the other protection against phase inversion, then if a qubit flip happens, then I'm not protected, okay? Can I protect my qubits against both kind of errors? Well, the answer is yes, but I need a slightly more complicated code, which is called the short code, okay? And in this case, I need to use 9 qubits. This is not the least the least amount of qubits that I need in order to protect against both kinds of errors. There are other quantum error correcting codes. In fact, there is one with 5 qubits, which protects against both kinds of errors. That is the minimum possible. But I'm going to show this one here because it's easier to understand with what we know about the other quantum error correcting codes. So what we do basically here is to first use one of the codes, and then with the physical qubits that we are using, the 3 physical qubits that we are using to implement our code, we use the other code, okay? So here you see that this first part here is exactly the coding that we use to protect against phase inversion. And then in each of these parts that we have here, we use the code that protects against the qubit flip, okay? So here you can see this as the encoding in the qubit flip code of a plus, okay? This is the encoding with 3 qubits of a plus, and this is the encoding of a minus, a state minus, with the 3 qubit code that protects against qubit flips, okay? So I'm using first a code. I go from logical qubit to 3 qubits that are going again to be logical, and each of these qubits is again encoded as physical qubits, okay? This is what is called concatenation of codes, and you can do it many more times. Again, you can consider this as a logical qubit, which is encoded with another code of 3 qubits or 5 or whatever, okay? So this is a typical construction. And I'm not going to go into the details, but the idea is that now you can measure syndromes for both codes. For instance, if you want to check whether there is a qubit flip, you use this syndrome, which you can see it's a repetition, 3 repetitions of the circuit that we use to measure the syndrome with 3 qubits. So this is measuring a qubit flip in these 3 qubits. This is measuring a qubit flip in these 3 qubits, and this is measuring a qubit flip in these 3 qubits, okay? So since I'm using a concatenation of codes, then I use the syndrome in each of the blocks that corresponds to the code that I'm using. And I can do the same to detect inversion of phase, but with the syndrome for the inversion protecting code, phase inversion protecting code. And here, notice that since I'm using for the part of the phase inversion, I'm using logical qubits, which in turn are encoded as 3 different physical qubits. In order to measure the phase inversion syndrome, I need to use 3 CNOT gates and 3 CNOT gates, because this is one logical qubit and this is another, the second logical qubit. This is one logical qubit and this is another logical qubit, okay? You can check the details, but the syndrome is, the syndrome computation is exactly the same. But now I need to take into account whether I'm using logical or physical qubits. And in this case, I'm using 3 physical qubits for one logical qubit, okay? And with this, the good thing is that, well, maybe you can think that we are only protecting against phase inversion and qubit flip, but there may be other errors. Well, the thing is that with this code, we can protect against any possible error that occurs on just one qubit. Why? Because I'm not giving you here the most general model of errors. There are more general errors, but imagine that we are dealing with, and this works also for that kind of error models, but imagine that the error that we are considering is just a unitary operation on one of the qubits, a general one qubit gate that occurs without us wanting it on one of the qubits. We know that this gate can be expressed as a linear combination of the identity, the X gate, the Y gate, and the Z gate, okay? So it's a linear combination of errors that we know, well, no error, which we do not have to protect against, error of qubit flip that we know how to protect against, error of inversion, phase inversion that we know how to protect against, and then this Y error, which is a combination of the phase inversion and the qubit flip, okay? And then when one of these gates acts on one of the qubits, what we have is a superposed state, which when we measure or when we compute the syndrome, it's entangled, each of the possible errors, it's entangled with the corresponding syndrome, okay? And we can use the combined information of the corresponding syndrome in order to correct any of these errors, okay? I think that the best way of seeing this is, again, visually. I could not fit all the syndromes, all the possible, all the needed qubits in one circuit, because the maximum number of qubits in Quirk is 16. So I divided this into measurement of the qubit flip syndrome and the phase inversion syndrome. But in practice, you would need both at the same time. Okay, so let me open this, change my screen, and probably I need to make this smaller, like that, for instance. Okay, so this is the part that corrects against errors of the qubit flip type. Okay, so well, I have a Y here, but let me use a not here, and you can see that now if the error occurs on one of the first three qubits, then the syndrome that changes is this one here, okay? And if I have an error in the second block, then the syndrome that changes is this one here, and the same for the third block, okay? And notice that, well, this is the same syndrome that we had in the case of the simple qubit flip code, but now 3 times. But also notice that if I have a Y error, for instance here, then I get here a syndrome that is the same as if I had an X here, okay? So this is something that we need to think about, but remember that if we have an X there or a Y there, the syndrome that I obtain here is the same. So this might be a problem, because then maybe I cannot differentiate between an X and a Y error, and this can be problematic. But let me go now to the other syndrome, which is the phase inversion syndrome. And I need to change my browser again. Okay, so this is the circuit for measuring the phase inversion syndrome. And notice, I'm going to start with the set. Notice that here again, what I obtain, in this case, I have 3 qubits. These 3 qubits implement just one of the logical qubits of the code. So if I have here an error in any of these 3 qubits, the syndrome that I obtain is exactly the same here. It's exactly the same here. If I have an error here, the syndrome is the same. And if I have an error here, the syndrome is the same. This could be problematic, but it's very easy to see that a set error in any of these qubits can be corrected exactly with the same operation. It's, so at the moment of correcting the error, I don't care where the actual error happened, okay? Because if I apply a set to any of the other qubits, if I apply a set here, for instance, then the error, the two phases cancel because I have -1, and this gives me 1, okay? So this is not a problem. And notice also that if I have a Y error, then I have exactly the same syndrome as if I had a Z, okay? But if I have an X error here, I have not syndrome. I have 0, 0, okay? So now, in order to correct an X, a Y, or a Z syndrome, error, I check both the syndrome for the qubit flip, the syndrome for the phase inversion, and if I have syndromes in both, it means that the error is a Y. If I have only syndrome in the qubit flip, then the error is an X. And if I have only syndrome in the phase inversion, then the error is a Z. And if I have no syndrome, then there is no error, okay? So with this combination of codes and with this combination of syndromes, I can protect against all these types of errors, okay? This is not the only code. There are other different codes, but this is one that I think it's very helpful in order to understand the ideas that are used in quantum error correcting codes, okay? Questions about this? No? Okay, so with this, we can encode information and protect it against errors by measuring these syndromes and applying the corresponding correcting operations. But we also want to be able to apply gates to these states. And one possibility would be to encode the state, protect it against errors, then decode it, and then apply a gate, and then encode again, and so on. But of course, that is, well, of course, much slower, and also could introduce many errors because I have to apply all these gates in order to encode and decode. So the good thing is that with this kind of error correcting code, I can apply what are called logical operations. So I can transform the information, I can apply gates directly to the logical qubits. I don't need to go back to the decoded state in order to apply gates, but I can apply gates to all the physical qubits that are encoding the information to have an operation that is equivalent to a unitary gate on the logical qubit, okay? So for instance, notice that if I have this encoding for the 0 state here with the short 9-qubit code, and if I apply a set to all the qubits at the same time, then this is going to change. This is going to apply a phase of -1, -1, -1. This is going to change to minus. This is going to change to minus. This is going to change to minus, okay? So now what I have is exactly this state here. So by applying the set operation, the set gate to all the qubits at the same time, I have implemented an operation that at the logical level is exactly like an X gate, okay? And you can also check that this is an exercise for you, that if you apply an X gate to all the qubits at the same time, then what you implement is a set gate at the logical level, okay? And these are ways of implementing these operations without needing to go back to the decoded state, but we can do it just in the logical circuit. So I have here a comment. Circuits become more complex. Errors can occur in any place. Where do you apply error correction? Any general strategy for that? Yes, I have just answered that. Okay. You apply gates without encoding and decoding all the time. Yes, that's the answer. The problem with these operations, which are called traversal operations, because we apply the gates to all the qubits at the same time, is that there is a limitation in how many operations you can apply in this way. There is a theorem which is called the Eastin-Neal theorem that says that in any quantum error correcting code with some implementation of these logical qubits, you cannot implement all the logical gates or all the operations that you need for universal computation as traversal gates. There is at least one of the gates that you need in order to have universal computation that cannot be done traversally. And then you have to apply other techniques. For instance, Shor also defined a very complicated way, well, a more complicated way of doing, for instance, Toffoli gate on this 9-qubit code in a fault-tolerant way, so the errors that do not propagate from one block to the other. Okay, but there are other techniques. For instance, gate teleportation. If you remember from the second, I think it was the second lecture, I told you that this gate teleportation could be also used in order to implement logical gates in error correcting codes. I'm not going to go into the details because they are a little bit more complicated, but if you want to take a look at that, I can provide some pointers, and it's not much more complicated than we have studied. But there are other techniques that you need to apply in order to implement these logical operations, also what is called magic state distillation. Well, there are several different techniques that you can use in order to obtain what we want, that is fault-tolerant quantum computation. Okay, I will talk about that in a minute. So we have studied this 9-qubit code. We see that we can protect information about any kind of error. We can implement logical gates. This is very nice, but it seems a little bit ad hoc. I mean, it seems that, well, we have been thinking about these codes, and Peter Shor came with this idea, but well, is there any other code? Is there any systematic way of studying this? Any other possibility of codes with different properties? Well, there is a lot of literature on this topic. It's very beautiful. It's also from the mathematical point of view, very interesting. It has to do with, of course, the classical theory of error correction, but also with group theory, for instance. I'm not going to give you the details because I think it's more advanced than the prerequisites that we said this course was going to have. It's above the linear algebra prerequisite, but I want to give you at least an idea of what you can do in order to study more general quantum codes. So the idea is to use this formalism that is called the stabilizer formalism, which has to do with the kind of operations that do not change the state that you use in order to encode logical qubits. Okay, so for instance, if we think about the qubit flip error correcting code, remember that we were encoding 0 as 3 zeros and 1 as 3 ones. And you can easily check that if you apply any of these operations to these two states, they are going to stay the same. They are not going to change. Of course, this is the identity on every qubit, so of course it's not going to change. But for instance, this operation here is going to introduce phases of -1 in this case. Well, it does not change any of these qubits, but it's going to introduce phases of -1 on both the first and the second qubit, okay? And they are going to cancel. So all these operations stabilize the states of the code. So they do not change. And also you can see that if you only consider these two operations, by multiplication, you can generate the others, okay? In fact, these operations here form a commutative group, an abelian group, and they are generated by these operations here. And it's also important to notice that these operations here always have eigenvalues which are either 1 or -1. And combining all these ideas, we can extend the number of operations or the definition of the code by studying which products of Pauli operations fix all the words that we are using in order to encode the logical qubits, okay? And that is what is called the stabilizer group of the code. And for instance, for the short code, you can see that the stabilizer operations are these ones here and the ones that are obtained by combinations, multiplications of these ones. And you can use these operations in order to study properties of the code. For instance, what are the errors that you can correct, different properties of the operations that you can implement logically. You can do many things. And in fact, it is easy. I'm not going to go into much detail about this, but it's easy to define the circuits for the syndromes that seem to be a little bit complicated in the cases that we have studied. But if you have the generators of the stabilizer group of the code, you can use this construction, this beautiful construction here, in order to obtain how to measure the syndromes. So this formalism is very powerful, not only for studying quantum error correcting codes, but for other quantum algorithms. And in fact, I'm going to mention it in a different context in a few minutes. And it can be used in order to study codes in the general situation. In fact, the most popular quantum error correcting codes that are being studied now in order to implement them in the future to have error correction in quantum devices are what are called surface codes, which are a particular case of stabilizer codes. And here you see, for instance, the implementation of one logical qubit with these many physical qubits, in which the operations that stabilize the code are defined with these green and yellow figures that we have here. So for instance, if we have this green figure, it means that the operation which is a set on this qubit, this qubit, this qubit, and this qubit stabilizes the code, okay? And then we use the black qubit to measure the syndrome of this generator. And here you have the circuit. Well, I don't have time to explain this, but you can check that this circuit follows directly from this construction here. What I want you to know is that this kind of codes, the surface codes, are the ones that are being considered now to be implemented in future generators of quantum computers. You see that you need a lot of qubits just to implement a logical one, but they also have good properties, and they can be implemented with the kind of chips that we have today, in which the connectivities between the different qubits, because you have to apply CNOT gates here, are neighbor to neighbor. Okay, so these are considered in now for future generations of quantum computers, because they fit well with the kind of hardware that we have and we expect to have in the future. All this is studied in order to obtain what we call fault-tolerant quantum computing. This is also a topic that would deserve a complete lecture, but just let me mention that the idea is similar to the things that I was telling you before, that we give a model of the errors. We suppose, for instance, that the errors occur with a certain probability and they are independent and not more than one error occurs at a given time. And then with some mild conditions on the properties of the code and on the error model, it can be shown that you don't need to apply too many of these concatenations of codes in order to reduce the probability of error as much as you want. Okay, so the decrease of the probability of error goes down exponentially, while the number of gates in your circuit and number of qubits that you need only grows polynomially. Okay, so this is a nice property, and this is what we call the threshold theorem. If the error of the code is the error of the hardware is below a certain threshold, that depends on the code that you are using, and if the errors satisfy a certain conditions that you impose in your model, then you can decrease your probability of error as much as you want without having a circuit that has an exponential increase in the number of qubits and gates. Okay, and this is the holy grail of error correction in quantum computing. Okay, so I don't know if there are questions about this. Okay, so to finish, I would like to talk a little bit about where are we in quantum computing and what we can expect in the future. And to talk about what is the current situation, of course, we need to talk about what is quantum supremacy, what has been achieved, and what does it mean for practical quantum computing or for the near future or the near term of the field. Okay, so quantum supremacy has been defined. Well, you also know that this term of supremacy has some controversy, but is widely used. Sometimes I will use supremacy, sometimes I will use advantage, but the idea is that it refers to that moment in which a quantum computer, a real quantum computer, is able to perform a task in a much smaller amount of time that the best supercomputer, classical computer would take for the same task. Okay, so it's a practical demonstration of a situation in which a quantum computer beats the best classical computer at a certain task. Okay, and it is important to notice that the task needs not to be practical, needs not to be something that we can use to solve a practical problem or to create some application in whatever field. Okay, it's only a task in which a quantum computer is much better, solves the task much faster than any of the classical computers that we have. Okay, of course, we could try to attain quantum advantage or quantum supremacy by using, for instance, Shor's algorithm to factor an integer. If we could have an integer of, let's say, I don't know, 10,000 digits or something like that, and factor it with a classical with a quantum computer, then we could check the result with a classical computer. This is something that we can do, and we can certify quantum supremacy because we do not have any algorithm that is able to factor 10,000 digits integer. Okay, the problem with that is that Shor's algorithm requires quantum error correction, and we are not at at that moment yet, because as you have seen, for instance, with these super surface codes, some of the proposals need up to 1,000 physical qubits per logical qubit in order to be able to have a logical qubit that is protected against any kind of errors. And then in order to use Shor's algorithm for factoring the integer, we would need again thousands of logical qubits. So we would need millions of physical qubits, and we are very, very far away from that. So the idea is to try to use a different task, which might be not so well-defined or so practical or so easy to check as factoring an integer, but that we can do with current quantum devices, okay? And this is exactly what Google announced that they have, researchers at Google announced that they had attained a little bit more than 1 year ago, okay? The famous quantum supremacy achieved by Google. So what did they exactly do in order to show this quantum advantage, this quantum supremacy? They did not run Grover or Shor or any of these algorithms that we have studied. What they did was to use the quantum computer to run circuits. This is exactly what a quantum computer of this quantum gate-based model does. It runs gates on qubits and then measures the results. So they thought, well, let's use a quantum computer to run random circuits and then check if what we are obtaining is compatible with what we expect from theory, okay? And there is a wide theory of the results that you can obtain when you run random circuits. The problem here, or the situation here, or the advantage over classical computing is that we do not know how to simulate quantum computers efficiently with classical computers. We don't know, given a random circuit, how to run that circuit efficiently in a classical computer. This is something that we, and in fact, there are several different results mathematically proven. For instance, the work by Aronson and Chen, which shows that is this task of simulating quantum circuits on classical hardware, it's impossible unless you have what is called a collapse of the polynomial hierarchy, which is something similar to discovering that P is equal to NP. This is something that we think is very, very, very unlikely. And this is not exactly the same, but is related to that idea. And we don't expect that to be true, okay? So sorry, there is a question by Richard Polivka. Thought the supremacy is reserved for classically impossible, proven by theory and task, and the advantage is reserved for the much faster. Yes, you are right. In some of the literature, advantage is only for, yes, a weaker version of supremacy, but the problem is that the term supremacy is so politically loaded that some people have been campaigning about for eliminating this supremacy term and using advantage or something like that. And some people argue that, as you say, supremacy is much stronger than advantage. It doesn't convey the same meaning, okay? But in some contexts, the term advantage is used as synonym to supremacy, and in other ones, as you say, it's reserved for something weaker. Okay, so there is some problem with the terminology there, but you are right. Okay, so as I was mentioning, what Google did was to run these circuits, and it has been proved that we don't expect to be able to find a classical algorithm that is efficient for running these random circuits, and then check whether they were in fact sampling from the expected distribution that you would have if you had a perfectly working quantum computer, okay? So to design the experiment, you need to be careful because there are situations, although in general, we do not know how to simulate with a classical computer quantum circuits. There are situations in which we have efficient algorithms for simulating quantum circuits even with a lot of qubits, For instance, one situation in which you can do that is, of course, if you have a lot of qubits, but only blocks of them are entangled with each other. So imagine that you have 5,000 qubits, but the qubits are only entangled with one with another. So the only pairs of qubits are entangled, and this block is not entangled with the other two qubits, and is not entangled with the other one. So then you can just separate the blocks that are not entangled. You can simulate each of these circuits independently, and then you can obtain the perfect simulation of the circuit by running these little circuits and then combining the results. Okay, so you need entanglement. You need entanglement between among all the qubits in the circuit. Okay, and that is why in the case of the circuits run by Google, they use these control set operations here, first in the horizontal direction, then in the vertical direction. Okay, so after several layers, they have entangled all qubits with each other. Okay, so they are all entangled in the whole circuit. Okay, you also see here Hadamard gates and then some rotation gates on T gates. Okay, but it's important to notice that you have entanglement that quickly spreads over all the circuit, because if you do not have that, then it's easy to simulate each patch of the circuit independently and then combine the results. So you need entanglement, but entanglement is not the only ingredient that you need in order to have something that is difficult to simulate classically. Because there is a very nice result which you can prove by using this powerful stabilizer formalism that I told you about. This is one of my favorite results in quantum computing, because I think it's very beautiful, and it shows how the representation of the information matters a lot when you try to simulate quantum circuits. So this theorem, which is called Gottesman-Neal theorem, tells you that if your circuit only has gates from the set, the Hadamard gate, the NOT gate, the C0, and the S gate, and combinations of these gates, for instance, if you combine these gates, you can obtain the Z gate, and you can obtain the Y gate and other gates. But if you only have these gates, then you can simulate the circuit with a classical computer efficiently. Okay, and the trick here is to represent the states not with the state vector that would need an exponential number of amplitudes, but with the representation with the stabilizer formalism. Okay, so each state can be defined, each of the states that you reach with the application of these gates can be defined uniquely with a polynomial number of stabilizers, of operations of these Pauli tensor products, and then you operate with that representation. And it's incredible that, well, even if you have a highly entangled state, I will show you an example in a minute, then you can simulate the circuit classically. Okay, so you need to be careful about that. You need to include, for instance, the T gate here, the T gate. Notice also that here, if you replace this S gate with a T gate, then you have universal computing. And universal computing is something, quantum universal computing is something that we think we won't be able to simulate classically. Okay, so just a change of this S gate with a T gate takes you from the realm in which you can simulate classically to a realm in which you cannot simulate classically anymore, or we think we cannot simulate classically anymore. Okay, so provided you construct these circuits in that way, there are these theoretical results that show that sampling from the distribution that you obtain, the distribution of results of strings that you measure by taking a random circuit, follows a certain theoretical distribution, which is related to what is called the Porter-Thomas distribution. And it's very difficult to sample from that distribution with a classical algorithm. In fact, it can be shown that there is a measurement that is called the cross entropy, that it's either in the perfect simulation of quantum circuits, it should give you 1, and with a uniform distribution instead of the real distribution of the strings that you obtain from the random circuits, it should give you 0. Okay, so this is a way of measuring whether you are simulating the circuits in a quantum way, or you are doing something that is not close to what you expect from the simulation of the circuits. So you can measure this cross entropy for your circuit, and then if it is close to 1, you are doing very well. If it is close to 0, then you are not doing anything that it's really quantum. You are not simulating the circuit. And it can be shown that even a small advantage over obtaining that value of cross entropy 0 is a signature of doing something that is quantum, okay? And that you could not do with a classical algorithm. And this is exactly what the researchers at Google did. And you see here that this cross entropy is going down with the number of qubits and also with the number of cycles, which is this number of layers that you have of different gates, 1 qubit gates and 2 qubit gates. But they showed that even in the case of 33 qubits, which is what they used, they estimated that they have a cross entropy that is close to 0, but is several sigmas above 0. And this is signature of quantum supremacy. Okay, this is something that we do not expect to do with a classical computer. And in fact, they estimated that a classical computer would take several tens of thousands of years to do the same that they did with these quantum computers in 300 seconds, okay? The article is quite easy to read. There is also this other article that I have linked here that explains this idea of the cross entropy, the Porter-Thomas distribution and all that. And I think if you are interested in this, you will be able to read it and understand a lot of what is going on. But I want also to mention this challenge that IBM posed to this quantum supremacy achieved by Google. So they said that, well, this figure of 10,000 years that Google mentions in the paper is not correct. You could simulate classically these circuits that they are running with a much faster algorithm. And they computed an estimation of what this algorithm would take for the same tasks that Google were using in their computer. And they showed that, for instance, for 53 qubits and a depth of up to 35 or 30 something layers, you could simulate this not in 10,000 years, but in about 6 days. Okay, which is much more than 300 seconds or 3 minutes or whatever Google needed with a quantum computer, but it's much less than 10,000 years. And there's been some controversy about this, okay? So I want to mention that, of course, still the advantage, if not supremacy maybe, of the quantum computer is clear, 300 seconds or 5 minutes or whatever against 6 days. Also notice that they, the researchers at IBM also computed estimations of what they would need for 1 qubit more. And you see here that the growth of this is exponential. I mean, for 53 qubits, you need more or less half what you need for 54, okay? And the same is true for the other number of layers. So it is clear that when you add a qubit, the time that you need gets multiplied by 2. So there is an exponential growth. So even with this algorithm proposed by IBM, if instead of 53 qubits, you would have 73, then the time that you need gets multiplied by 2 to the 20, which is more than 1 million. Okay, so again, if Google or other researchers can reproduce the same kind of task, but with more qubits, we have something that even with this algorithm could not be done classically. Okay, so why this estimation by IBM? What is the kind of algorithm that they propose to use? Well, the idea here is that if you try to simulate the circuit with the state vector, you need 2 to the 53 amplitudes. And this is something that you cannot have in RAM. You cannot have in the memory that you use for your computations. But you could have this in a hard drive. This is what, or in a lot of hard drives, okay? So you could use this state vector, access this state vector, but with much more memory, okay? So what IBM proposed was to have a lot of hard disks and work directly with the state vector, because the algorithm that Google used to estimate these 10,000 years is what is called a simulation of the circuits in polynomial space. So you don't need to have all the amplitudes at the same time, but you need to do much more operations, because what you do is basically to consider that there are some gates that provoke a bifurcation in the tree of computations. For instance, when you have a Hadamard gate, then you have a superposition. And if you have a circuit like this one, the amount of branches that you have to follow begins to grow exponentially, okay? So the idea is that in order to use the state vector, you would need the amplitudes of all these different possibilities. If you cannot work with all those different possibilities, what you can do is to follow each of these branches one by one, okay? And then go back, backtrack your steps and follow other branches, okay? And this you can do in polynomial space, so you don't need to have all the amplitudes at the same time, but it takes much more time, okay? But what IBM said is, well, if you have a lot of hard drive, you still can work with the whole state, okay? So this is the controversy. I want to go quickly now because the time is running out. Some people asked me about these new announcement of quantum supremacy, or in this case, they are using advantage, but with the meaning of supremacy, achieved by several researchers at different universities and research institutes in China. And in this case, what they use is a different approach. They don't use a program, a universal quantum computer, like in the case of Google, but they use what is called a photonic implementation of boson sampling. And what is this boson sampling? Well, in this task of boson sampling, which was proposed in 2011 by Aronson and Arkhipov as a way of showing quantum supremacy, you have a network of linear optic devices. like beam splitters and mirrors and things like that. And then you feed some photons at the input, as the input of your network, of your linear optics network. And then you measure, you have some detectors of photon detectors at the other extreme of the network. And then you detect photons at some places, okay? Of course, this is a quantum evolution of the different superpositions of possibilities for the photons. So what you measure is probabilistic. And it has been shown that sampling from this distribution, it's difficult in practice. It's difficult for classical computers because it is related to what is called computing the permanent of a matrix. Of course, the operation of the linear optic devices that you have can be described by a unitary matrix. And then in order to see the different possibilities that you can obtain for the detectors, depending on the photons that you input at the beginning, you need to compute the different paths that the photon can follow. And these different paths are related to the rows and columns of the unitary matrix and involve the computation of what is called a permanent, which again is difficult to compute classically. Estimating this or computing this would efficiently provoke a collapse of the polynomial hierarchy. Okay, so this is exactly what these researchers did, was to sample these distributions with an implementation of a random network of these photonic devices, and they showed that their results were close to the theoretical distribution. Okay, the problem here is that they didn't use this boson sampling directly, but they used a different version in which the input is not of this kind, but is called a squeeze state. And you have what is called Gaussian sampling. And the problem that has been raised now that the paper has been published is that for that Gaussian version, for that Gaussian boson sampling, we do not have the same theoretical results that we have for pure boson sampling. So there is some challenge there to whether it would be possible to simulate or to sample from this distribution with a classical algorithm. So there is still development going on there. Okay, so to finish up, I would like to show you some roadmaps that different quantum companies, companies doing quantum research, have published in the recent months. And well, more or less, all of them aim at having by the end of the decade, by 2029 or 2030, depending on how you define decade, up to 1 million qubits in their devices. Okay, so this is something that is also common for other companies. For instance, IBM is also aiming at this 1 million qubit goal. They propose to have more than 1,000 qubits by 2023. Okay, so well, there are other companies like IonQ that talk about algorithmic qubits, which are qubits with good properties. Okay, so I think we are going to see quite a lot of development in the following years. And my wish list for this near term, or for a more near medium term, would be first to have more confirmation of quantum supremacy, this experiment done by the researchers at China, other groups working in different approaches or confirming the same approaches. Of course, it would be very interesting to develop practical applications of these niche quantum computers that we have now, maybe with quantum machine learning, maybe with chemistry simulations, maybe with applications in high energy physics. Of course, we also expect to have advances in qubit technologies, increasing the coherence times, decreasing the errors, in order to be able to implement this fault-tolerant quantum computing. And of course, I also would like to see the development of new quantum algorithms with, if possible, exponential speed ups over classical versions, okay? If we end up having these quantum fault-tolerant computers, but we do not have many algorithms to use with them, that would be a pity, okay? So, well, especially since I work in the algorithm development field, I think this is also very interesting. I don't know if there are questions. I'm already 5 minutes over time. Well, so then I would like to say thank you very much again for your attention, for your interest, for the many questions and feedback that we have received, for the people that have answered the survey. This has been really an incredible experience for me to share my passion for quantum computing with so many people. And well, I really want to say thank you. I also want to thank the people which were in charge of the technical part, especially Melissa, Pascal, Lloyd, and also of course, I want to thank the CERN's Quantum Technology Initiative, especially Alberto Di Meglio, for all the support for organizing these lectures, and I wish them all success in the future. And with that, thank you again, and I give the floor to Alberto Di Meglio to have some closing words.
Yeah. Thanks, Elias. Thank you very much for this series. So, of course, I mean, all good things must come to an end. So this brings to the conclusion of this 7-part lecture series on practical introduction to quantum computing. This was indeed the first series in the education and training program of the new Quantum Technology Initiative here at CERN. And indeed, it was quite successful and well received. Also, thanks to not only to the knowledge and expertise of Elias, of Professor Combarro, but also to the way he has managed to convey this knowledge and his passion to us. I mean, we received a lot of comments related to this, and so not only the content was extremely interesting, but the way you explain this, I mean, makes it look so easy. You know, at the end of every lecture, I have the feeling that, hey, everything is clear and fantastic. Then reality hits. I have a lot of things to study and understand myself, but this was really an amazing series of lecture. So thanks, really thanks a lot for this. So we are designing the program for next year, for 2021. And of course, we welcome any idea, proposal, comments that you know, everybody, the community around us wants to give us, provide to us for the future. And of course, the survey that Elias has mentioned many times, it's one of the ways of giving us comments. So please, by all means, fill the surveys, but also, you know, contact us anytime on the Quantum Technology Initiative, the QTI mailing list, and information channels. So before closing, I also would like to thank the audio-visual team in the CERN IT department for the great work in the backstage, in the back behind the scenes. It took a lot of hard work to manage the different channels and the recording, the live streams, the webcast, different formats. So really, thank you very much for the support. And thanks to Melissa Gaillard, the CERN IT Department Communication Officer, for being a great executive director of this series, week after week, managing all the different components of these streams and the people and the announcement. That this was a really, really great work. And of course, thanks again to Elias for this amazing ride in the past few weeks. And of course, thanks to everybody who has attended these lectures, both live and recorded. It started with almost 2,000 people. Of course, it went a bit down, but we are still having an audience of many hundreds of people following the stream and the recorded lecture on the CERN CDS and in YouTube, which shows a great interest and great, great enthusiasm for this, sort of emerging fields, given the many possibilities that are appearing around us. So this, of course, encourages us to continue on this path, not only on the scientific and technical research, but also on the education, training, and sharing activities with the broad scientific communities. So thanks a lot, everybody. And I would like to wish everybody as much as possible a great end of this rather weird 2020. And a year 2021 with hopes for the future and much better health for what is going to happen in our lives in the future. Thank you very much. Thank you and goodbye. Thanks.